Welcome back, everybody. I would like to now give the floor to Linda Speight from Reading University. Linda, when you're ready, you can share your screen with us.
Thank you. I'll just do it now. Okay, so hopefully you can all see that. Is it working?
I think it's coming. Yeah.
Yeah, excellent. Okay, so yeah, my name's Linda Speight and I work at the University of Reading, and I'm going to talk a little bit more from kind of the end user end of forecasting for flash floods and surface water rather than the development of the model end. This is a presentation that involves work from a number of people. So it's got work from the University of Reading, also people from Scottish Environment Protection Agency, University of Strathclyde, RAB consultants, and across a previous research programme called the Flooding from Intense Rainfall programme, which was a UK-funded programme looking at very similar things that I think you're looking at real PEP. So it's interesting to see how you're carrying forward some of the ideas we looked at in that. So since we can't kind of meet for coffee, I thought I'd start with a quick who am I and why I can contribute to this presentation. So as I said, I'm a postdoc at the University of Reading. I'm currently looking at forecasts for humanitarian decision making and forecast-based financing. So that's kind of separate to this work, but things that relate to what we're talking about today is I've recently completed a review of surface water flood forecasting for SEPA, that's the Scottish Environment Protection Agency. And I've been involved in, as I said, the Flooding from Intense Rainfall programme. And also I've worked as an operational flood forecaster up in Scotland, and I developed a surface water forecasting pilot that was used during the Commonwealth Games in Glasgow. So these are all examples of the work that have fed into this presentation that I've done today. So as I said, what I want to talk about is kind of the very end of the end-to-end forecasting chain. So ensuring that forecasts that we produce as scientists actually lead to action. So I'm going to start by talking about closing the circle of the end-to-end forecasting chain, thinking a little bit about what do end users need from a forecast, and comparing that to what scientific limitations are and what we as scientists might feel comfortable being able to produce and say. And then looking at a little bit about different approaches to operational surface water flood forecasting. So the presentations this morning have been talking about flash flooding. I'm talking here about surface water flood forecasting because my experience to date has kind of been looking at flooding in cities, but I think the UK is quite unique in that we do define surface water flood forecasting differently to flash flooding, whereas really they're kind of a continuum. If you've got a small watercourse coming through a city, you're going to get flash flooding, and it might be combined with surface water flooding. It's very difficult to differentiate them. So though the terminology is different here, I don't think the approaches are really. So here I've got a very simple end-to-end forecasting chain. So starting off with observations, driving a weather forecast at one end, which you then put through a surface water forecasting model. You visualize that in some way, make some kind of assessment, and then communicate that assessment out to decision makers who hopefully will take some action based on it. So this all looks very neat and organized, but it's quite linear. We're going from kind of the left-hand side to the right-hand side, whereas in reality, there's a lot of feedbacks in this. So you've got uncertainty in your observations and weather forecasts leading to uncertainty in the weather forecasting model. In your assessment of hazard, so you might define hazard as a 1 in 200 year event or something, but that's very reliant on the quality and length of observations that you've got to start with. How you do your post-processing. So a few of the other presentations this morning have talked about post-processing, and how you visualize the data will inform your hydrometeorological assessment. How you present your hydrometeorological assessment will influence how people turn that into information, how much confidence they might have in the model. Because if people don't have any confidence in your model or what you're saying, they're not going to take any action on it at all. Then the next point we've got is if you take action on a model, well, that's actually going to affect your impact. So when we're talking a little bit about how do we evaluate how good our models are, we've got an impact-based forecasting model, and we said that so many properties are going to flood, but actually the action taken is to put up some flood defences. Those properties won't flood, so it's hard to evaluate the model. So this final big purple arrow here really is saying, based on what action we expect people to take, should imply, should influence the decision about what type of surface water forecasting model we want to develop. And that's what I'm going to be talking about throughout the rest of this presentation. So what we want to do to ensure that the forecasts we produce do have some kind of effective action is close the circle of that end-to-end forecasting chain. So some of the work I did in terms of the flooding from intense rainfall programme was to review how well people thought that we worked together in that programme, how well we had the meteorologists and the hydrologists linked together. And it was interesting in Karina's presentation there, where she was talking about the different groups waiting for feedback from the hydrology team to feed back into their own bits of rainfall and meteorological forecasting. So I think that was really good to hear that, because that's something that perhaps we could have done more of. But good output from the review there was people saying actually where hydrologists and meteorologists have worked together, they'd started to close some gaps in understanding between disciplines. And one of the things that came out of that programme was, even though we are all focused on the same end, so forecasting intense rainfall or convective rainfall or flash flooding events, whatever we want to call it, we perhaps have different language, different priorities, different things we're looking at. So it's really important that we do speak to each other and work together. And also these quotes on the right-hand side of the screen from more end-user people saying how important it is to put the weather forecast in the context of decision makers to make sure that the science that we're doing isn't wasted and actually has beneficial impacts down the chain. So there's a couple of references there if you want to look up any more details about that. So what do end users want from a surface water flood forecast? So this is feedback from the development of the model we made in Glasgow for the Commonwealth Games, also another research project that was done in Yorkshire in the UK last year. And it was good to see that these are pretty similar to the ones that Marina Helena was mentioning earlier on this morning. So things we found people wanted was time for proactive preparation. So that could be clearing trash screens, installing flood protection, most importantly, getting extra staff involved so you can set up an incident room, knowing something's coming in advance. So 6 to 24 hours, ideally 12 hours, but sometimes just as little as 1 to 2 hours was helpful. Most importantly, they wanted guidance on event timings, what locations would likely be impacted and what those impacts might be. Key thing here was, even though as scientists we might not feel very happy about it, end users did want to hear about the low likelihood but high impact events, so kind of the black swan scenarios, but so they could enable proactive low regret actions to be taken in case those major events did happen. And then something that's really easy to do, but perhaps is often forgotten, is to communicate a stand down message to say, actually, we thought big thunderstorms were going to happen today, but they've moved on, they've gone somewhere else, or they've dissipated. You can all stand down. So that's fine, that's great. Really useful to have these conversations at the start of a project about what people want, but what is feasible? Because we all know that there's high uncertainties around predicting location, timing, and impact of these flash flood events. I know Brian Golding at the Met Office talks about the maximum you could forecast on a deterministic forecast would be a 10 by 10 kilometre rainstorm at 3 hours ahead, which is helpful, but it's not going to give those kind of location details that end users want. So therefore we need probabilistic forecasts, they're essential, and also impact-based forecasting to really help with communication. So hopefully I'm preaching the converted here, but if we've got a forecast which just tells us the rainfall totals, so this is a forecast from the Met Office for the UK in August with rainfall totals of 30 to 40 millimetres up to 60 millimetres, doesn't really mean that much to many people. But when we convert it into impacts, you can see chance of fast flowing deep water bringing danger to life. This is what's really useful to people and enables them to actually take proactive action. But I think it's important to remember, though, that real-time flood modelling is really at the limits of computational ability. If you want to do really detailed models with lots of probabilistic forecasts and run through kind of a real-time inundation model, you're not going to get a lot of lead time in terms of being able to communicate those results out for people to take action. And also the terms of staff resources. So our experience when we did this in Glasgow for the Commonwealth Games was that because we're dealing in the probabilistic realm, there's a lot of uncertainty involved. that actually the staff resource to interpret and communicate the forecast was quite high. So as a forecasting service, you need to be really committed to doing this to have enough members of staff that can sit there and take phone calls from people to help them understand a little bit more about what the forecast actually means for them. So SEPA, Scottish Environment Protection Agency, are committed to developing their service water flood forecasting, and they recently asked us to review what different approaches have been taken. So I'll go on to that in the next few slides. Basically, it's important to remember that different people have different ideas of what they need. It's not really a one-size-fits-all solution, so that means that there's space for us to develop lots of different approaches, all equally valid, but with different strengths and weaknesses in them. So this report for SEPA is available online. That's the full report to SEPA. There is also a journal paper that's recently been accepted in Wires Water, so that should be available in the next month or so. But SEPA asked us, what should we know about if we want to improve surface water flood forecasting? Quite an open, broad question. We also prepared in that report a review of rainfall forecasting capabilities, but I think that's been discussed in the previous 2 days of the conference, so I'm focusing here on the flood forecasting aspects. So what we did is classified all different types of approaches to surface water flood forecasting, and these are approaches that are operational or nearly operational. So not those that are being developed in science research projects, but those which have actually been used in practice or could be used in practice. And classified these into 3 groups: empirical-based threshold scenarios, hydrological forecasts linked to pre-simulated impact scenarios, both at a national scale and a regional scale, and then hydrological forecasts linked to real-time hydrodynamic simulations at the urban scale. And there's very few examples of this, and there's lots of examples of these first 2. So you can see more details of all of these examples, either in that report to SEPA or in this journal paper when it comes online. But I'll just quickly run through the 3 different approaches. So in both empirically based rainfall scenarios, so in this case you have some observed rainfall or water level. So you might have small sensors or upstream gauges that you could use, or you could have a rainfall forecast ensemble, or indeed a deterministic forecast. And you see what numbers are in there. Compare those against pre-calculated thresholds. So say, based on an event that happened last year, we know that flooding starts to occur when the water level or the rainfall amount gets above this, and then you can issue an alert that flooding is possible in the local area. These are really quick, easy to use. Any advances in your forecast ensemble rainfall immediately benefit your alerts and your warnings. But they're usually used alongside other approaches, so they're not very reliable in their own right and usually require expert knowledge and experience to interpret them. So these are kind of a first guess approach, and they're quite well used as that kind of heads up that something's happening. We need to look in more detail at some of our other modelling approaches. So then we come on to pre-simulated impact scenarios. So these take account of the fact that across most of Europe now, we now have to have a library of flood inundation and impact maps. So we have to know where in our countries is susceptible to flooding and what the impacts might be if floods occur in those areas. So how can we make the best use of that data by linking it back to the forecast? So if we've got a forecast for a certain amount of rainfall, we can then run that through a real-time hydrological model, because they often run quite quick and they're already set up to run operationally by the national forecasting services. And then we can make some assessment about how we can link that through to the flood inundation maps. So when we did this for Glasgow, we made the assessment that the effective rainfall, so the rainfall which didn't infiltrate into the soil, was the same as being used to generate the static flood inundation maps. When you do this with an ensemble of rainfalls, you get however many maps that you had ensemble members, and then you can assess a risk matrix out of it. You can do this across a large area or across a small area of a city. So this is really useful because it is quick. It means you can do it in real time during an event and still maintain some lead time. However, sometimes you might actually be looking at smaller scales than really is appropriate based on the uncertainty in the rainfall forecasts. So you might produce a really nice looking map at kind of city level impacts, but is it really appropriate to be communicating city level impacts when, as meteorologists and hydrometeorologists, we know that the uncertainty in forecasting these kind of convective rainfall events is quite high, and it's really quite hard to say exactly where they're going to occur. So we need to consider the appropriate reporting scales for these kind of scenarios. And then the final set we looked at was hydrological forecast links to real-time hydrodynamic simulations. And this is limited really at the urban scale based on how long it takes the models to run. So these all took short-range forecast rainfall, so normally looking at nowcasts, or and the operational case we've got here looks at deterministic nowcasts, but potentially you could do it with an ensemble of nowcasts. And you actually take that forecast rainfall and run it for a real-time hydrodynamic model. And this has the advantage that it gives you both modeled flood depth and extent, but also looks at velocity. So particularly for these flash flood events, a lot of the injuries and deaths are caused because of the velocity of the water, not just where it is. So if we can identify where the fastest flowing water is, then that's really helpful for communicating that out and making flood resilient decisions. However, there's a massive computational requirement to doing this, and it's not really possible to do this with probabilistic forecasts, certainly not with NWP forecasts beyond a few hours of lead time. So this is still an emerging capability, and it's got high computational runtimes. So that was a rapid run through of our kind of assessment of different approaches, just to show you that there are lots of different approaches out there, and the benefits and disadvantages of doing those will really depend on what you're looking for. My experience of doing this, when we did it in Glasgow, we used the lookup table approach based on existing flood maps, and we produced these kind of impact-based grids looking at impacts across Glasgow itself. So what we found is what people really want to know is exactly when and where impacts will occur, so they know where to get people. If you're looking at a city scale, city council could put all of its resources on one side of the city, flood happens on the other side of a city, but because there's so much rainfall and flooding, they can't get those resources across town. So it's really important to get this location detail. So that's what they want. But actually, although we might sit here and go, oh, well, people don't really understand this probabilistic forecasting and the limits of convective forecasting, I don't think that's the case anymore. I think people who are making operational decisions based on this do understand that it's really difficult to forecast these kind of thunderstorm events. A key thing we had was consistency across scales. So you might say, although across the whole of the southwest of Scotland, there's going to be some flooding, whether we looked at in Glasgow itself, we would say actually there's no risk in Glasgow. Whereas if you compare those two events, people are saying, well, why does the regional-based forecast identify a problem and not the city-based forecast? So this is where you come with this high staff resource for interpreting and communicating it. And then less is often more. So this is something I find quite difficult to deal with as a scientist. You've got all these great models, you can pull all these interesting bits of information out of them. But actually, when it comes down to decision makers, they're not interested in that. They just want to know when and where impacts might occur. That's it. They don't want to know the ins and outs of it. So quite difficult sometimes to stop sharing the uncertainty and to think about whose decision it is to make an assessment on the uncertainty and then just communicate a message rather than a whole range of possible scenarios. Oh, my slides are frozen, sorry. Right, okay. So finally then coming on to conclusions. I think it's important to say that convective permitting numerical weather prediction has enabled development of surface water flow forecasting. So five years ago, we wouldn't have had any of these kind of surface water forecasting models. Would have just been looking at those kind of threshold-based approaches. But because we've got more confidence in the forecast models, and we've also got better computational computers, so we can run models faster, it's actually possible to do something more about surface water flood forecasting now. But it's important to remember that such models cannot and possibly will not deliver timely and reliable flood forecasts in the same way that we're used to for fluvial and coastal models. So therefore, we need to have a real change in thinking about how we deal with this kind of flooding and how we deliver forecasts, how we make decisions and how we communicate those decisions. However, with a clear understanding of strengths and limitations, there can be an effective tool. And there's a little nice video there, if you want to watch it probably in your own time, about the nowcast forecasting at Loughborough University. And there's the police force at the end saying that the models really passed the test for them because people who've been out in the field up to their knees in floodwater have found it useful. And I think those kind of comments really helpful when we're doing this kind of work to understand what it is that's important. But my key thing, and the thing that I end up talking about quite a lot in these type of presentations, is that successful surface water flood forecasting models require interdisciplinary approaches because of the uncertainties throughout the forecasting chain. We really need to be working very closely with meteorologists and the hydrologists and the hydrometeorologists, and also the scientists and the decision makers all working together to understand the limitations and how uncertainty affects the chain and how we can communicate a clear message to end users. So thank you. That was a bit of a rapid run through, but if anyone's got any questions, I'm happy to answer those, or you can get in touch with me after the presentation.
Thank you very much, Linda, for this really nice talk. I'd like to open the floor here at the speakers room. So does anyone would like to ask a question? Yes, Stefan, please.
Yeah, thank you very much for the very interesting talk. I have one question. I mean, on the technical side of the forecasting system and the forecasting approach, the computational challenge comes up often, right? And you mentioned also several times in your presentation. I would like to understand, so the computational challenge, is it more related that we do not have, I mean, we have massively parallel, resources, right? They're available, the machines they exist. So my question is it the problem that we do not have access to these machines, or we do not have access to enough of these machines? Or is it that we do not have the software to use these machines efficiently? So where really is the challenge coming in here?
Okay, so in my experience of this, when we did surface water forecasting for Glasgow and the Commonwealth Games, we're working really closely with the Met Office. So the Met Office has got supercomputer resourcing, so potentially we could have run models on their resourcing. But they also have a very clear structure during the day of what models run at what time. So if you want to communicate a message out to end users and they need that information by 9 o'clock in the morning, you're not necessarily going to be able to have runtime on the supercomputer, the results to have processed, all of that to have happened for you to deliver a message at the right time in the day. So there's that issue that the resources are there, but are they available at the right time? The other issue is ownership. So I think this is maybe a bit of a political issue. So who runs these kind of models? Is it the Met Office, the meteorological organisations, or do the hydrologists want to maintain some kind of ownership of these models and therefore the ability to edit them, add new details into them? And I think then you come up out of a bit of a resistance that operational hydrology doesn't have access to those kind of computational resources in the same way. So this is where we need perhaps where it comes back to this idea of a rethink about how we deliver this kind of operational forecasting. And it's going to be different to how we deliver fluvial and coastal flood forecasting. And I don't think we're quite there yet in the mind space of how we go about doing it effectively. So yes, the resources potentially are there, but they're not accessible in operational real time.
So I hear a little bit between the lines, the optimal way would be that flood forecasting, hydrologic forecasting has their own operational centers, also with their own computational resources, and that are of course coordinated with the Met offices and so on. But okay, thank you. I would agree actually very much. Yes, thank you very much. Bye.
A question here.
Yes, please.
Thank you, Linda, for this very nice presentation. My question is about the communication challenge. Higher the detail in space and time of the forecast, higher the risk of rising false alarm, false warning. This is the case where the crying wolf syndrome might really matter. Based on your experience, what is the response and the the impact of this type of wrong forecast on the stakeholders?
Yeah, so I think it really depends who your stakeholder is. If it's kind of a professional body, so say the fire service, who are going to be going out rescuing cars or people trapped in water, you can do training with them before the event happens to understand the limits of the forecast and what may or may not happen, so then they can plan accordingly. But if you're communicating directly to the public, or newspaper headlines get attached to your forecast, that's when you have this crying wolf problem that you don't want to be saying too often that something's going to happen, because people will just run with that and don't understand the uncertainties. So I think we all need to get better at communicating, understanding who we're communicating with, and developing relationships before events happen, so that we've got kind of communication chains and also understanding of each other's roles and what people need from our forecasts and what kind of level of risk they're prepared to accept in them.
Thank you very much.
Thank you very much, Linda.